Welcome to Shri Learning Academy. Let's simplify thread scheduling. Imagine this. You open a browser, start a video call, play music in the background, and type code in an editor. Everything feels smooth. Nothing seems stuck waiting its turn. Behind this smooth experience, something very small but very powerful is making constant decisions every fraction of a second. That decision maker is thread scheduling. Thread scheduling is the process by which the operating system decides which thread gets to use the CPU when it gets it and for how long. We already know that a thread is the smallest unit of execution inside a process. Multiple threads can exist inside a single process, sharing the same memory but doing different tasks. Now, the big question becomes this: when there are many threads ready to run, how does the OS choose which one runs next? This is where thread scheduling comes in. Think of the CPU as a single microphone on a stage, and threads as people waiting to speak. Only one person can speak into the microphone at a time. Thread scheduling is like a moderator who decides who gets the microphone, for how long, and who goes next. Without this moderator, everyone would try to speak at once and nothing would make sense. In modern systems, thread scheduling is usually handled by the operating system kernel. The kernel keeps track of all runnable threads and selects one based on a scheduling policy. This policy defines the rules of selection. The goal is not just to be fair, but also to keep the system responsive and efficient. Let us look at what the scheduler actually sees. From the scheduler's point of view, a thread can be in different states. A thread may be running on the CPU right now. It may be ready, meaning it wants to run but is waiting for CPU time. Or it may be blocked, meaning it cannot run yet because it is waiting for something like input or a lock. The scheduler only chooses from threads that are ready. Now imagine a simple example. Suppose a web browser process has multiple threads. One thread handles user input like mouse clicks. Another thread loads web pages from the network. Another thread handles rendering the page. If the scheduler gives too much CPU time to the network thread, the user interface may feel slow. If it ignores the rendering thread, the page may not update smoothly. So the scheduler must balance these threads carefully. This brings us to an important idea. Thread scheduling is closely related to responsiveness. For interactive applications, the OS often gives higher priority to threads that interact with the user. This is why your system responds quickly when you move the mouse or type on the keyboard, even if heavy background work is happening. There are two broad ways thread scheduling can happen. One is non preemptive scheduling, the other is preemptive scheduling. In non preemptive scheduling, once a thread gets the CPU, it keeps it until it finishes or voluntarily gives it up, usually by waiting for I/O. This approach is simple, but it can cause problems. If a thread runs for too long, other threads may starve and the system may feel frozen. In preemptive scheduling, the operating system can interrupt a running thread and take the CPU away from it. This happens using a timer interrupt. When the timer fires, the OS saves the state of the current thread and may choose another thread to run. This allows fair sharing of CPU time and better responsiveness. Most modern operating systems use preemptive scheduling. You may remember context switching from earlier topics. Thread scheduling and context switching go hand in hand. When the scheduler decides to switch from one thread to another, the OS performs a context switch. It saves the current thread's registers and execution state and loads the state of the next thread. This happens very fast, but it still has a cost. That is why schedulers try to make smart decisions and avoid unnecessary switches. Another key concept here is time slicing. In many systems, each thread is given a small slice of CPU time, often just a few milliseconds. When its time slice expires, the scheduler may switch to another thread. This creates the illusion that multiple threads are running at the same time, even on a single CPU core. Now let us talk about priorities. Not all threads are equal. Some are more important than others. A real-time audio thread, for example, must run on time or you will hear glitches. A background update thread can afford to wait. To handle this, the scheduler assigns priorities to threads. Higher priority threads are chosen before lower priority ones. Consider a music player. One thread reads audio data, another updates the playlist UI, another checks for updates in the background. The audio thread must have high priority. If it does not get CPU time on time, the sound will stutter. So the scheduler favors it. This does not mean low priority threads never run. It just means they run when higher priority threads are not urgently needed. Thread scheduling also depends on whether threads are user level or kernel level. With kernel level threads, the OS scheduler directly manages each thread. This allows true parallelism on multi-core systems since different threads can run on different cores at the same time. With user level threads, the OS may only see one process and the thread library does the scheduling inside that process. This can be faster but less flexible. We discussed this difference earlier, so here it is enough to remember that kernel level threads give the OS more control over scheduling. On multi-core systems, scheduling becomes even more interesting. Now the scheduler must decide not only which thread runs next, but also on which CPU core it should run. This is called processor affinity. Sometimes it is better to keep a thread on the same core it ran on before, because its data may still be in that core's cache. Moving it to another core may slow things down. Modern schedulers take this into account. Let us look at a practical scenario. Imagine a server handling thousands of client requests. Each request may be handled by a separate thread. Some requests are quick, others involve disk access or network delays. The scheduler constantly moves threads between running, ready, and block states. When one thread waits for disk I/O, another thread immediately uses the CPU. This keeps overall throughput high. At the same time, the scheduler must avoid starvation. Starvation happens when a thread never gets CPU time because others always get chosen first. To prevent this, schedulers often use techniques like priority aging, where the priority of waiting threads gradually increases over time. One important thing to understand is that thread scheduling policies are different from CPU scheduling policies you will study in the next module. CPU scheduling focuses on processes at a higher level. Thread scheduling focuses on threads, often within the same process. Many ideas overlap, but the scale and goals are slightly different. In simple terms, thread scheduling is about fairness, responsiveness, and efficiency at the thread level. It ensures that small units of work get their chance to execute without stepping on each other. When you later study synchronization issues like race conditions and deadlocks, you will see how scheduling decisions can affect correctness. A tiny change in which thread runs first can completely change program behavior. That is why understanding thread scheduling is so important. So every time your system feels fast and responsive, remember this. Countless tiny scheduling decisions are happening silently, choosing which thread runs next, keeping everything in balance, and making modern multitasking possible. That is it for this video. See you in the next one.